Very good morning, my dear students. Welcome back. Let us discuss numericals based on self-induction concept. Alright? And the next concept we'll be moving in this session itself after finishing few numericals, and there are some sufficient classwork questions are also available today. Alright? And let's start. The first question. Find the change in current in an inductor. Change in current in an inductor. So here itself you should understand DI you need to find. Of 10 Henry. Right? So L value is how much given? So it is 10 Henry. In which EMF induced is 300 volt. EMF is 300 volt. In 10 raised to minus 2 seconds. So there is dt is also given 10 raised to minus 2 seconds. Also find the magnetic flux change, right? So what is the aim here? So it is clearly visible. Aim is to find d phi. The last session, it was completely about the self-induction, and we have found the formula for the self-induction E is equal to L into dy by dt, di by dt. E is induced EMF due to the self-induction. L is coefficient of self-induction or self-inductance. Okay, so di by dt, di change of current, dt is the change in time or time interval. Di by dt on a whole, it is called rate of change of current. Just now find the change in current. See, there are two aims here. So E is equal to d, so di we need to find out, and d phi also we need to find. Well, let's find di first. What is E? It's 300, which is equal to L. L is 10 into di. So that is unknown by dt. So dt is 10 raised to minus 2. When it goes to the numerator, it will be 10 raised to 2. Okay. So now here 10 raised to 2, 10 raised to cancel. So from here I can write di value is equal to 3 by 10 ampere. That's di. Okay. Now the question is about also to find the magnetic flux change, my dear children. So the magnetic flux change I could find out by using the formula called d phi by dt, which is equal to E. So this was our discussion, Faraday's law. Alright. So as long as there is a magnetic flux change, there will be an induced EMF production. So E is equal to d phi by dt. So this E is how much? It's 300 volt is given, and d phi finding is our aim, and here also the same thing goes. So dt is 10 raised to minus 2. So in the denominator, if I write 10 raised to minus 2, when it goes to the numerator, that will be 10 raised to plus 2. So it is 100 gone here. So the answer, a magnetic flux change will be 3 Weber. What is the SI unit of magnetic flux? Weber. Understand? So like this you can solve the questions. Right? Now, look at this part. AB is a part of the circuit. So this AB is a part of the circuit. Find VA minus VB. Where is AB the part of circuit here? You can see this is A and this is B. This AB is the part of the circuit. Okay. And VA minus VB we need to find out. So the potential difference, these 2 points we need to find out. Okay. Potential difference between these 2 points. And if I make a circuit here, carefully see. If I make a circuit here, as the current is flowing in this direction, so I can imagine A is at high potential, this is the point, and B is at low potential, and this is called VAB. And you know, VAB is equal to VA minus VB. That's what the potential difference between these 2 points. Understand? So VAB is equal to VA minus VB, and that's what our aim. Right? Now, the first case, If a current 2 ampere is flowing and it is constant, imagine the current is flowing here 2 ampere which is constant in the first case. Listen, the first case we are doing here. Okay. First case circuit, I'm just redrawing here for your better understanding. So the first case circuit, carefully see. So there is an inductor here. So there is a cell here, and this is the resistor here. So this is 1 Henry and this is 5 volt and this is 2 ohm. So this is my point A and this is my point B, and here interestingly there is 2 ampere current, constant current flowing here. And this is my battery of potential difference VAB. Alright. Now, here I am writing, carefully see, as the current passing through this inductor, this is the inductor. So what is the induced EMF produced? It's 0 because current is constant. Your induced EMF formula is what? E is equal to L into di by dt. So when this current is constant, look at here, d by dt of constant, it is 0. 0 into L is 0. So final answer will be 0. So there is no induced EMF produced here. Right? So just 2 ampere current will be passing through this inductor. That's it. Then strike this positive terminal of the cell, then the same 2 ampere will be passing through this resistor and reach back to the negative terminal here. And by using Kirchhoff's voltage law here, so what I can say, there is a loop A, B, C, D. Let's see the loop called A, B, C, D. What is Kirchhoff's voltage law tells us? The potential difference across the resistor and the potential difference across the cells, the sum of all the potential differences across the cells or across the resistors will be equal to 0. And let's start from A. So there is no resistor or no cell is involved here. If the current is passing, if the current passing through the inductor is increasing or decreasing, then only induced EMF will be produced. Now induced EMF is 0. So then just the 2 ampere current passes through this inductor and strike this positive terminal according to Kirchhoff's voltage law and sign convention. So we need to write it is -5 because our current direction and loop direction are same and our current direction is striking the positive terminal. So that's why -5 we need to write. After that, so the current direction and this is my loop direction. Okay, current direction and loop direction is same. So here the potential difference across this is IR. So that's called -IR. So -I into R. Okay, so the current is moving in this direction and strike the negative terminal. So that means it is plus VAB is equal to 0. Alright, clear? So now this VAB is equal to, so this is -5 -4. When it goes to the other side, +5 +4. So you get 9 volt. What is that? 9 volt. Alright, when current passing through, it is constant, remember. Now here comes a very important numerical. In most of the NEET exam, the question was asked like this, right? So what is the question? And look at here, my dear students. A current 2 ampere and it is increasing at a rate of 1 ampere per second. Current value is increasing at a rate of 1 ampere per second. Okay? So let's start. This is A. There is an inductor here and this is the cell and the resistor and the point B. Okay. So look at here. So this is my VAB external source, positive terminal and negative terminal. So here current 2 ampere is passing and this is 1 Henry and this is 5 volt and it is 2 ohm, right? Let's discuss. This is the current is increasing. An increasing current passing through the inductor. Remember always, If the current passing through the inductor is increasing, what happens? The induced current will pass through this in the opposite direction. This is called induced current. Understand? The induced current is due to the self-induction phenomenon. I am writing this as IS. Induced current will try to oppose the growth of the current. If this is the direction of induced current, and listen, the induced EMF will be like this. This is induced EMF E. Okay? Clear? So the direction of the induced EMF is already represented with the diagram. So then induced EMF formula will be L into di by dt. Alright? So now this is the inductor will behave as a cell whose EMF is L into di by dt. Alright? Now you apply Kirchhoff's voltage rule. A, B, C, D. Same thing. By using Kirchhoff's loop A, B, C, D, let us apply Kirchhoff's voltage law. Here. This is what? The cell. Minus E, because our current direction is striking the positive terminal, minus E. Now it goes like that. Our current direction is striking the positive terminal, it's minus 5. And our current direction is in the direction of current here. Okay, in the direction of current. How much is the current? So I into R, minus I into R. So now our current direction is striking the negative terminal, plus VAB, which is equal to 0. VAB is VA minus VB. No confusion. The potential difference, that's what they're asking. Sometimes they'll ask you to find VB minus VA. So in that case, your answer will be minus 9 volt. Okay, so leave it. So come back here. So what is that? Your VAB is equal to this minus E comes to the other side. That will be plus E. Minus 5 plus 5. Minus 4 plus 4. And it is plus 9. Understand? Clear? So now your VAB is equal to E. E value is what? L into di by dt, my dear students. So plus 9. No confusions at all. This E, we are not writing any sign. Sign we had represented with this symbol itself. Right? So now L. What is L value here? It's 1 into di by dt. So that's called rate of change of current. See, it is increasing at a rate of 1 ampere per second. di by dt is 1 ampere per second. So this is called di by dt. It is not alone di or even alone dt. No, it is di by dt. Right? See here. Current is increasing at a rate of, means rate of change of current is given 1 ampere per second. So this value is 1. So this is 1 plus 9. So 1 into 1 plus 9 is 10 volt, my dear students. Alright. Clear? So if you really understand this, the next classwork question which I am going to give you, you will understand it very well. Right? Now, third case. What's the third case? The second case. What's my third case here? Third case is simple. The current 2 ampere and it is decreasing. Current 2 ampere and it is decreasing. The same thing, let me write here. So this is the resistor. So this is point A and it's point B here. Right? 2 ampere current. This is 1 Henry. It's 5 volt and it is 2 ohm and 2 ampere current is passing like this. So this is the battery you have, which is VAB. Okay. Same 2 ampere current is passing through it, but the current is decreasing. When the current is decreasing, the induced EMF will try to oppose the growth of the current. So that means induced current will be in this direction and the induced EMF will be like this. This is the induced EMF direction E. Now same by using Kirchhoff's voltage loop, A, B, C, D is the loop. Okay, A, B, C, D is the loop. Let us apply. So here, current is moving in this direction and strike the negative terminal. So that means we need to take positive. it goes like that and strike the positive terminal, we need to take minus. And the current 2 ampere is passing through 2 ohm in our direction of the loop. So that is called minus 2 into 2 is 4. So and we will be reaching to the negative terminal here. It's plus VAB, which is equal to 0. Okay. So now this is the third case we are doing. So VAB is equal to this plus E goes to the other side, that will be minus E, right? Minus 5 minus 4, it's minus 9. Minus 9 goes to the other side, that will be plus 9. So what I can write, it is minus E is L into di by dt plus 9. My dear students, remember here, so this minus sign is just from the Kirchhoff's voltage law we have got, but nowhere we have used E is equal to minus L into di by dt. We have just used L into di by dt because negative sign is the representation with this symbol of the cell. No confusions, right? Just practice whatever we have discussed. You could solve all the questions related to this. So now VAB is equal to minus L is 1 into di by dt is 1, because it is also very important. Here also the current of 2 ampere and is decreasing at a rate of 1 ampere per second. Here also current is decreasing at a rate of 1 ampere per second only. Okay, so 1 into 1 plus 9. So 9 minus 1 is 8 volt. Alright. Clear? So that's it. It's so simple. This is the most important numerical of the chapter. Most important numerical is this one. Alright. So let's see whether you could solve the classwork question or not. Right? Let's see your classwork questions. Alright. So these both questions are your classwork you have to do right away now. Let's look at the question. Same like the previous question here. There is a part of the circuit AB. The potential difference between this A and B you need to find out. And in this part of the circuit there is a resistor present and a cell present here, and there is an inductor is also present. You know, if the current is increasing at a rate of 1 ampere per second, what will be the potential difference between these two? When the current is increasing or decreasing through this inductor, it will behave as a cell with induced EMF, right? If the current is decreasing at a rate of 1 ampere per second, you should find the potential difference between these 2 points. You can check with these answers, but just follow the method what I have told you in the last class, last slide. Next question. A 35 volt EMF is induced in 0.32 Henry coil by a current that rises uniformly from 0 to I0. Generally, this I0 is called the maximum value of current. Maximum value of current. Or I can also say it's a peak value of current. What is that? So peak value of current. Okay. In the next chapter called alternating currents, you will understand what exactly the peak value of current. Okay. Now, the current is rising from 0 to I0 in 2 milliseconds. What is the value of I0? Okay. So this you can find. So by using the basic formula, induced EMF is equal to L into di by dt, where di is change in current. Di is what? Change in current. That's what the hint I am going to give you here. So di is equal to change in current. The final value minus initial value. That's what the hint I gave. I will not go into the details, right? Just a hint I gave, and you could definitely solve these 2 questions, right? Right now, just pause your video and try solving these 2 questions. Check with the answers and send me the solutions. I hope you understand it, right? All right. Now, the next topic in today's session is energy stored in an inductor. How come an energy stored in an inductor? That's an interesting question. What is this inductor? Now you will understand, right? So let's look at it. So there is a circuit here. In the circuit there is an inductor is present. There is an external source of battery with a key is placed in the circuit. This is the key and it is the external source of voltage V. And this, imagine the current I is flowing at any instant, right? Imagine at any instant dt, current flowing through this inductor is I. Remember, at any instant dt, the current flowing through the inductor is I. See, current flowing through the inductor is I. Imagine when we switch on, what happens? Slowly the current value reaches from 0 amperes to the maximum value of current. So which is, I can write it as I naught or okay, I naught. Now, so 0 ampere to I naught, it is slowly moving. When the current is increasing, it is moving like this. In this case, induced EMF you can find out. So induced current will be this way. This is induced current. So when it is the induced current due to the self-induction, I am just representing this with I suffix S. And this will behave as a cell of EMF E. Alright? You know, by using Kirchhoff's rule, I can also say that this is minus E plus V is equal to 0, and this I can write V is equal to E. Alright. So this V is equal to E, which is equal to L into di by dt. So this by using Kirchhoff's voltage law I have got it. Loop rule. Now, here comes the important point. The concept of inductor comes here. When the current value is slowly increases, there is an induced EMF which opposes the growth of the current, yes or no. For example, without this inductor, if the current is reaching to the maximum value in 2 milliseconds, with the inductor, current will reach the maximum value greater than 2 milliseconds. Greater than 2 milliseconds, because there is an opposing EMF is developed over here. This opposed EMF will try to will try to increase the time taken by the current to reach the maximum value. Even to reach that maximum value, so there is some external work is to be done on the charges to reach the maximum value. Okay, that external work is done by this external source. This external source need to work so hard to reach the current and its charges to their maximum value. Current means the flow of charges, rate of flow of charges. Alright, clear? Current to reach the maximum value, it has to overcome the induced EMF and reach the maximum value. So to overcome this induced EMF, there is some external work done is required. So that's what I'm writing here. So the rate of work done by external source is dW by dt. Alright? So the dW by dt is called power. Yes or no? dW by dt is called power. So power is equal to V into I, my dear students, where V is E, which is L into di by dt. Listen, L into di by dt. Okay. So what I can write into I? Sorry. V is L into di by dt into I. So dt gets cancelled here. So dW is equal to L into I into di. So this is at a particular instant. right? At a particular instant, the work done in moving the current through the inductor, which is acting as an induced EMF, which is acting as a cell. So the complete work done you get if you integrate this here. So if you integrate this, what happens? Let me remove this. If you integrate this, what happens? Integral dW is W, which is equal to L. L is the self-inductance of this inductor. So L is constant. Integral I dt, right? Integral I dt, I can write it as I square by 2. Integral x dx, x square by 2, right? So let me take the limits here. What are the limits? Current started from 0 seconds, I've told you, 0 ampere to maximum value the current is reaching. So I can write L into I naught square by 2, my dear students. L into I naught square by 2. What is this work done? I have told you already, whatever the work done, that will be converted into the form of energy. But here, listen, because of the self-induction, there is a magnetic field associated with this inductor. So that's called the magnetic energy associated with this inductor. Yes or no? Inductor is a solenoid, nothing else. Inductor is a solenoid. So when a current is passing through the solenoid will produce the magnetic field. And when there is a magnetic field, we can say that there is a magnetic energy associated with that solenoid. So here also the same thing. You know from where that magnetic energy associated? This only. Whatever the work done by the source, work done by this external source to overcome the induced EMF and send and push the charges to reach their maximum value of current. So that work done will be converted into the form of magnetic energy. Understand? So that's what I am going to write here. So this work done will be converted or stored in an inductor in the form of what? In the form of magnetic energy. So this I can write, this W I can write it as U, which is equal to U is what? Energy. Energy stored in what form? Energy stored in magnetic energy form, which is equal to half into L into I naught square. So in some books it will be written as half into L into I square. No confusions. Alright? No confusions. Half into L into I square. I is the maximum value. Whatever may be written here, that is maximum value only. Alright? Now, one more interesting point I'll tell you. Listen. So nowhere you will get all these things, my dear children. Is it the energy is similar to an expression called half mv square? 100% it is similar. And where this I naught is the rate of flow of charges, that means movement of the charges, and here V is velocity of a body. It's similar, anomalous, right? Sorry, analogous. Now, L and M. M is what? Can I say mass is the measure of inertia? Can I say mass is the measure of inertia? 100% I can write. So this term, whatever is analogous here, that must be representing the inertia. Self-inductance is the inertia of electricity. Did you remember this statement or not? Self-induction is the inertia of electricity. I told you so many times in the last class. That's what this is. Mass is measure of inertia, and L, self-inductance, is the inertia of electricity. That is what we had already discussed. Alright. Now, one more. From this, if L is constant, so then U is directly proportional to I square. If I is constant, so U is directly proportional to L, right? Depends on the constant what it is. So this where L is constant and this equation where I is constant. Okay. Here it will be U1 by U2. So let me write that also. U1 by U2 is equal to I1 by I2 whole square, and this U1 by U2 is equal to L1 by L2. Alright. Now, one more thing. The last part of this energy stored in an inductor will be, we know energy density per unit volume, which is equal to, right? So energy density per unit volume, this is energy density per unit volume is equal to half B square by mu naught. Remember, half B square by mu naught. B is magnetic field associated with this inductor, and mu naught is permeability in free space, right? You know the mu naught value, 4.2 10 raised to minus 7 Tesla meter per ampere. All right. So similar equation you have already learned. You might have, I strongly believe that you might have already learned in parallel plate capacitor. All right. Energy stored in the parallel plate capacitor is electrostatic energy. Understand? So here magnetic energy density per unit volume. There electrostatic energy density per unit volume U suffix E, which is equal to half into epsilon naught into E square. Remember this. This is also energy density per unit volume only. Okay, clear? So these are the two equations which are similar, and these are the two equations which are similar, my dear students, right? So let's solve. This is one of the important topics from the chapter. Let us solve some numericals based on energy stored in an inductor now. Two different coils of self-inductances, 16 millihenry and 12 millihenry. At a certain instant, the current in the two coils is increasing at the same rate. What does it mean? Current is increasing at the same rate means di by dt value is same. Remember, di by dt value is same. And the power supplied to the coils is also same. So power supplied is also same. Find the ratio of induced voltage. Induced voltage is induced EMF, and we have the formula of induced EMF, E is equal to L into di by dt. As di by dt is constant, I could write E is directly proportional to L. From here, E1 by E2 is L by L2, and which is 16 millihenry by 12 millihenry. Millihenry cancelled, right? And it is that 4 4s and 4 3s, and your answer is 4 by 3. What is this? This is the ratio of induced voltages, right? Now, ratio of the currents, it is also a question. Ratio of the currents. How you can find the currents here? Where there is no concept of current is involved here in the equation. E is equal to L into di by dt. There is no concept of current is involved. Right? Now, energy stored in two coils. Energy stored formula is half into L into I square. Here current values you have, but energy ratios we don't have. Okay. Here you see from this, U is directly proportional to Li square. So you need to find the ratio of energy stored in the two coils, right? So U1 by U2 is equal to L1 by L2 into I1 by I2 whole square. Our aim is to find here I1 by I2. You can find it, but by using U1, U2 and L1, L2 values. At this point, we don't know U1, U2 values. How you will find the I? Read the question once again. Read the question once again. This is how you need to approach towards the numericals. Two different coils of self-inductances, 16 millihenry and 12 millihenry, At a certain instant, the current in the two coils is increasing at the same rate. I told you di by dt is same and the power supplied to the two coils is also same. So power supplied. And let's take this power supplied is equal to V into I. Can I write like this? Why? Because here V is induced EMF. Okay. When this P is constant, I can say E is inversely proportional to I. From here, E1 by E2 is equal to I2 by I1. What is E1 by E2? It is just 4 by 3. From here, I1 by I2 is 3 by 4. So, first answer is 4 by 3. Second answer is 3 by 4. Right? Now, you know I1 by I2. It is easily find out now, right? So, U1 by U2 is equal to L1 by L2. What is L1 by L2? 16 by 12. Okay, that is equal to 4 by 3 into I1 by I2. It's 3 by 4. So, 3 by 4 whole square. 3 by 4 into 3 by 4. 3, 3, 4, 4 cancel and it is 3 by 4. And this answer is also 3 by 4. Alright, my dear students, is it clear? Now, this is the class work question now. So, total including this, there will be 3 class work questions I have given. I hope the previous 2 you have solved. Let's see here. A current of 20 milliampere is passing through a coil of inductance 500 millihenry. Alright? Find the magnetic energy stored in the coil. This is the first case. You can find by using the simple formula U1 is half into Li square because L is there, I is there, you can find U1. If the current is halved, find the new value of energy. Simple, if the current is halved. So in the second case, what happened? Half into L into current is halved. I became I by 2 whole square. Solve these two and you definitely get these answers. First answer and the second answer, your answers need to be like this. Clear? And let's get ready for your assignment of 5 important questions. All the very best.